I like to call this little puzzle here the mystery of the walrus. So we now know the answer to the mystery of the walrus, that is, why the walrus behaves one way and integers behave another. But we want to understand really why. And so to get to that, I'm going to explain a little bit about how computers work under the hood. Now this is a little bit of a fib, be warned, and in the book I lay out a little more of an honest story, but for our purposes this is basically true. So anything you want to store on a computer is stored in so-called memory. And that memory, whatever it is it an arrangement of atoms? Is it like crystals that have been imbued with the power of the gods? Who knows? But whatever it is, ultimately that memory is, all information is encoded as a sequence of ones and zeros. Okay? So some examples. In a computer, the number 72 is usually stored as 01001000. Or as another example, the number 205.75 is often stored as 01000011, etc., with 32 more zeros up here. Then the letter H, for example, it's often stored as 01001000, and you'll notice that's actually the same as the number 72. So you have the same encoding. And the computer knows how to interpret those bits based on the particular context. Okay? And as a last example, the value true is often stored as a bunch of zeros followed by a 1. Now, it's not always the case that true is always stored this way or 72 is always stored this way, but these are the most typical representations. Okay? And so if you're really curious about this stuff, this class isn't really going to dig deep into representations, but suffice it to say that given anything that you can name, you can certainly come up with some sequence of ones and zeros and say it refers to that thing. Okay? So each Java type, right? So when you have a Java variable, even though the letter H and the number 72 have separate representations, the type tells the Java interpreter how to interpret it. So if I have a variable that's of type character, then when it sees this sequence of bits, it's going to be thinking about the letter H. But if I have an integer variable, it will know to treat it as the number 72. So it turns out that in Java, there's 8 primitive types. There's byte, short, int, long, float, double, boolean, and char. And we're not going to spend a ton of time talking about each of these types. But be aware, these are the 8 primitive types. Okay? And so, again, as I alluded, we're not going to say why is 205.75 equal to this sequence of bits. That's actually a class that follows this one called 61C. But if you're curious, you can go reading, and the book gives some links if you want to get ahead of the game. But in this course, all I really care about right now, I want to understand why does the mystery of the walrus resolve in the way it does, and this is a piece of information that I think is really useful to us in understanding that. Okay? So, what we're going to do is let's use this simple model of declaring a variable and combine that with our knowledge of bits to really reinforce the fundamentals we'll need for the mystery of the walrus. So here's some code. I'm going to run it in a moment. Okay. So when you declare a variable of a certain type in Java, say int x or double y, what happens is your computer is going to set aside exactly enough bits to hold a thing of that type. It's got some billions of bits that it can use, and it's going to say these bits are going to get to be int x, these are going to get to be double y. So an int, as it turns out, is always 32 bits. Okay? Even if you only are storing a small number, it still gives you 32 bits. Or if you declare a double, you get 64 bits. That's just how it is. Okay? And so Java, what it will then do is it's going to create some kind of table that says, okay, anytime I see the symbol x, that means I'm referring to this piece of information. And Java does not write anything in particular into those boxes. So it's got this huge sequence of bits. It says these get to be x, and it just records, okay, from now on when I see x, I mean this memory. And so if I look at this visually, after running this int x, I get a box of 32 bits. And after running double y, I get this box of 64 bits. Now note that I haven't put anything in here. Now there is something in there. Because memory is just some physical object out there in the world, the memory will contain some sequence of zeros and ones, but Java does not let you actually access the information that's laying around. It's sort of like if you pick up a piece of paper off your desk because you need to scribble a quick note, there may already be something on there, but you usually don't care about it, right? Because you just want to write down a phone number someone's telling you or whatever. So there might already be something there, but Java will not let you see what's already there. There's just no way to see that information. So in this case, what I'm saying is that Java doesn't let you access a variable that's uninitialized. So if I tried to print x or y at this point, it would say no, not allowed. Okay, so that's declaration. So now let's talk a little bit about assignment. So whenever I say x equals some big number like this, what Java will do is then fill it with all of the bits that correspond to this number. And it turns out that the 32 bits that correspond to this negative number here is this sequence of bits. And when I say y equals this right here, well, what it will do is fill that with the 64 bits that represent this particular number. Okay? And of course, there's some code under the hood that knows exactly how all this works. There's a whole stack of interesting abstractions that go down to the hardware level, and that's really 61C's purview to say just how these bits happen. But for our purposes, to understand the mystery of the walrus, this is what you should know. We get 2 boxes, then they get filled up with bits. All right? So what? All right? Well, we're getting there. But before we get deeper, I want to introduce a little simpler notation. So whenever you look at this, this is probably, if nothing else, a little intimidating, right? It's just some giant long sequence of bits. So this box notation that I've introduced, I'm now going to make it even simpler and call it simplified box notation. And in this notation, what we're going to do is instead of writing out the memory box contents in binary, because I can't read that, you can't read that, we're just going to write out the value in human readable symbols. So when I say x equals this, I will just fill the box with that. Okay? That's going to be our notation, and it happens to be consistent with the Java visualizer we use in this class. Okay, so now that we know about bits, I'm now ready to tell you why the mystery of the walrus resolves the way it does. And that's because it follows what I'm going to call the golden rule of equals. Okay? So given 2 variables, y and x, when I say y equals x, I'm just taking all the bits in x and copying them into y. Okay? So let's look at this in action. Now keeping in mind our picture of simplified box notation. So when I say int x equals 5, I get a box that contains the number 5. And when I do int y, I get a box, not pictured here because the visualizer chooses not to do so. And so when I say y equals x, it's just going to copy those bits that are in x into y. So there they go, they're in the box. And now if I say x equals 2, remember what the golden rule of equals does is it says it takes these bits and puts them in this box. So what are these bits? It's the number 2, and it puts them in which box? This box. So there's no change to y because that's not what the golden rule of equals says. It says take this box and fill it with bits, not this box. There's 2 distinct boxes. Fill this one up. Okay. And that's the answer to why integers behave the way they do. So the natural follow-up question is, well, what about walruses? And we'll get there in a moment.